Welcome back, friends, in this session. In the previous session, we have discussed that we cannot select the zero sequence current as a reference. We cannot select its axis as a reference or symmetrical axis so that we can determine which side the fault should be detected as a forward direction and in which side it should be detected as a reverse direction. We discussed that about the V0 that we cannot select as a symmetrical axis. So we take a symmetrical axis as an axis to determine which side should be forward and which side should be backward. And we try to analyze our system. For example, this is our system. We analyze that okay, mostly the zero sequence current during the fault be in this direction. So we take a symmetrical axis so that we take this angle from the zero axis, from the zero reference. It's little declined because we decline it to take the majority of this zero sequence current should be diagonal. It should be perpendicular to our symmetrical axis, so that we can because this part is only taking a part for detection the direction and for the mostly operations of this our system, our method. We selected this axis as a symmetrical axis, and for the system which is mostly inductive during the fault path, if the fault path is mostly inductive, so we take a little shift for this axis, and we decline this axis this direction because our zero sequence fault current will be in this direction, so mostly it should be perpendicular. Then the component, the perpendicular part on the symmetrical axis is more decisive for the fault detection and for detecting the forward or reverse direction. Now in this example, this side is the forward direction and this side is the backward direction. But the question is that we have some amount of the current, for example, this amount of zero sequence current during the operation. Even we have some zero sequence current. So if we select it as a zero, and if any value of zero sequence current be increased 2 ampere, 3 amperes, then our system will operate even though there is no fault. During the operation it will operate and it will trip, maybe it will pick up. So let's draw another line and another axis, so that this axis should prevent this in this direction between the symmetrical axis and our new axis should not operate, and furthermore in these directions it should operate, and also in the reverse direction in this area it should not operate. And after that, whenever the zero sequence current increases beyond this value, then it will operate and it will detect for the reverse direction. These two axes are called minimum polarization axis. For more clarification, let's view an example. In this example, the axes are drawn, and this one is our symmetrical axis, and also these axes are minimum polarization 3I0 for direction determination, that whenever it increases beyond this, so then the direction determination process will start. And we know here the power that here P greater than 0 and Q greater than 0, this is for positive sequence power. It is not for zero sequence power. The zero sequence power, we know that this is p-axis, we call it p0, and this is the q-axis, q0. But these ones are for the real, for the positive sequence power, because in this axis here becomes p and here becomes q. We tilted the zero sequence power by 90 degree, because this V0 mostly occurs at 90 degree of the positive sequence voltage. And some of another components, this direction is backward and this is reverse forward direction. Whenever this zero sequence current, this zero sequence current, here it is shown as a minus 3I0. The reason is that mostly in positive sequence current I1, and this I1, for example, in our system, this I1 flows in forward direction, in this direction. During normal operation, this we call it as a I, or normal current, that is positive sequence current. But the zero sequence current flows in the reverse direction, that is I0. This I0 in the reverse direction during the fault. So actually this current is in this direction. Relay will understand this is zero sequence current. This is the current which the CT, this CT detects actually, but the case is that we should give a minus, so the direction becomes in reverse, and it the relay can understand it as a lagging. This is what we discussed, that actually 3I0 in this direction, if this I1 be in this direction, the this is I1, IA1 we call it, IA1, this is IA0 in opposite direction. So actually here it is in opposite direction during the fault, but the relay should take it as a lagging value by V0, that is we give a negative to the value of 3I0, and this is the angle phi. We know that this phi is minus, and we know that our symmetrical axis is this axis. Which value of this current, this is I0, this I0, which value of this I0 we need? We need this perpendicular part, we need this component, the vertical component, or the V0 on the V0, the component which is coincides with the V0 axis. So this is 3I0 directional. We need this part, so we take the cosine of phi, cosine of phi for calculation, for measuring method, because the side value of an angle is cosine, and there's this phi correction, the correction value we'll discuss later, even though we have discussed in the previous session, but for more clarification we will clarify it furthermore in our discussion. Then this part is the minimum polarization zero sequence current for direction determination. Here it is taken as an example as a 0.03 amperes, and these two axes, that is defining alpha 1 and alpha 2, these are the alpha 1 reduction direction area, because during the fault what happens, some of the faults at the beginning of the fault it chooses a transient condition, it may be like this, and in this we should not define the direction, we should not furthermore operate our system because it's operation switching or something like that. So we give an axis here, two axes. These two axes, if the I0 be like in here, then furthermore it will not pass this axis and it will not determine that it is in forward direction. Also for the next for alpha 1 the same. Alpha 1 reduction direction area 2 degrees, and alpha 2 reduction direction area as a 2 degrees as a default. We should define it, we should enter these values for the relay, and we know that this part is reducing the capacitive part, because we have already discussed in previous session. If you do not understand, so let refer to the previous session. Here alpha 1 defines if the zero sequence current in nature is capacitive, and here it defines for the inductive part. If we want our system that it should not be very sensitive to any type of zero sequence current flowing in the system, so we increase this angle. If we increase this angle, our sensitivity for some of the misoperations in the system will be reduced, and also our sensitivity will be reduced, especially in the type when our system has more flashovers. So these flashovers will drastically with very high inductive part, if it be, then this amount of the current, the zero sequence current, will be like this. And if we do not increase the direction reduction area, these flashovers will be detected by the relay and it will have an operation which we don't want, that type of operation, for example.